All right, let's dive into a story about a math problem that was a total dead end for 2 full centuries. I mean, we're talking about something that the greatest minds in mathematics looked at and said, nope, can't be done. Until someone came along and claimed they'd finally cracked it. This is a story that really challenges what we think is possible.
And that idea is really at the heart of what we're talking about today. You see, for generations, there was this rule in math that was treated as an absolute, unshakable truth. But as we're about to see, some truths are just waiting for the right person to come along and ask, are we sure?
So for generations, you had mathematicians running smack into this unbreakable wall when it came to solving certain kinds of equations. They were taught, and they believed, that some problems just didn't have a clean, exact answer.
Okay, so what was this wall? Well, it has a name, the Abel-Ruffini theorem, and it dates all the way back to 1824. And what it basically said was, for any really complex equation, we're talking fifth degree or higher, there's just no single one-size-fits-all formula to get an exact answer using the usual tools like square roots or cube roots. For 200 years, this was considered gospel, a mathematical dead end. So, why? Why was it labeled impossible? Well, think of it like this. For the simpler equations, mathematicians had a set of keys, right? Things like square roots, cube roots, and these keys could unlock the answer every single time. But once you got to these fifth-degree equations, the internal structure of the problem just exploded in complexity. It was like a lock with constantly shifting parts. The old set of keys just didn't fit anymore, so the conclusion was the lock is unpickable.
And this timeline, wow, it really shows you just how heavy this problem was. From 1824 all the way to 2023, the entire mathematical world just accepted this limit. Sure, they found clever ways to get super close to the answer, with approximations, but they could never get the exact solution. For 2 centuries, that was just the way it was. Game over, or so they thought. But then, a modern mathematician comes along, looks at this 200-year-old wall, and doesn't see a barrier. He sees a challenge, an invitation, even.
This is Professor Murad Sultan Ezouidi, and he looked at this piece of history not as a final, definitive statement, but as an incomplete one. He had a hunch that the answer was out there. Everyone had just been using the wrong tools.
And his whole argument really boils down to this one quote. He suggested that Abel, back in 1824, didn't prove that these equations were fundamentally unsolvable. No. He only proved that the toolkit they had in the 19th century wasn't powerful enough for the job. And that is a huge, game-changing distinction.
So what was his new approach? He didn't just try to jiggle the old key in the lock a little harder. No, he went back to the drawing board and designed a completely new key, a whole new way of looking at the problem itself.
Now, this table really lays it all out. On the left, you have the classical methods, impossible, relies on approximations, accepts limits. But on the right, you have Ezouidi's theorem. It gets exact solutions, it's 100% verifiable. The really big deal, though, is at the bottom. It's a total philosophical shift, from accepting what seem to be inherent limits to rejecting what he calls mathematical fatalism. It's about refusing to believe a problem is impossible.
So how in the world does it work? Okay, imagine the equation is a big tangled ball of yarn. The old methods were like trying to pull on one string, hoping the whole thing would just unravel. It never worked. Ezouidi's method is completely different. It's a process of carefully turning the ball over and over, applying these specific steps that reorganize the yarn, loosen the knots, and reveal the hidden patterns inside. You do this over and over, and eventually, the ball of yarn practically unravels itself, handing you the exact answer.
Okay, that's the theory, but what does this new method actually do? What does the answer look like? Let's take a look at a real example. A 7th-degree equation, exactly the kind of thing that was supposed to be impossible to solve for centuries.
Just look at this thing. It's a monster, a 7th-degree polynomial. For 200 years, the idea of finding one simple, clean formula to solve this was a total pipe dream. It looks like an absolute beast of an equation.
And here's the solution after you apply Ezouidi's theorem. All of that chaos, all those huge numbers and high powers, they all just collapse into this one stunningly simple, perfectly exact answer. X equals -3. That's it. No endless decimals, no close enough, just -3.
Now, it's really important to understand, this doesn't mean Abel was wrong. What he did was incredible. It just means his work was a landmark within a certain framework. And now it seems that framework has just been blown wide open. It's about building on the past, standing on the shoulders of giants, not erasing their work.
And really, this whole thing leaves us with a pretty profound question, doesn't it? It just goes to show that sometimes the limits we think are fundamental are just the starting line for the next great discovery. If this impossible problem wasn't impossible after all, what else is out there, just waiting for someone to find a new key?